This is video 1 for the induction unit. So for this unit, I want you to be able to explain Faraday's law. I want you to be able to explain how electricity is generated, explain how AC, that means alternating current electricity, is different from DC or direct current electricity. And then for your math learning goal, I want you to be able to make calculations involving transformers. So, in the early 1800s, the only current producing devices were voltaic cells. You would know them as batteries. These would produce small currents by dissolving metals in acids. And again, these were the forerunners to our present day batteries. Then in 1820, Oersted found that magnetism was produced by, or could produce, or magnetism was produced by current carrying wires. So in other words, when electricity passed through a wire, a magnetic field was generated around that wire. So the question then became, could electricity be produced from magnetism? So then 1831, two physicists, Michael Faraday in England and then Joseph Henry in the US, each working independently and no knowledge of the other, they discovered that yes, magnetism could create electricity. So this has just completely revolutionized industry and our daily lives. So electromagnetic induction. So what Faraday and Henry both discovered was that electric current could be produced in a wire by simply moving a magnet in or out of a coil of wire. So if you take like a bar magnet and a coil of wire, and if you were to move this bar magnet in or out of that coil of wire, you would see that an electric current is being generated. So this device right here is called a galvanometer, and it simply detects electric currents. Very small electric currents, but it can detect electric currents. And notice that when the magnet goes in, the needle deflects one way. When it's pulled out, the needle deflects a different way. That's kind of important. Also, the magnet has to be moving. If the magnet is stationary, there is no current produced. So then, again, what they discovered was that voltage, which is one measurement of electricity, was caused or induced by the relative motion between the wire, coil, and the magnetic field. So if you did keep the magnet stationary, if you moved the coil, that would generate a voltage. So this voltage is induced whether the magnetic field of the magnet moves near a stationary coil or if the coil moves in a stationary magnetic field. Something else, the greater the number of loops moving in a magnetic field, the greater the induced voltage. So it may seem then that we're getting something for nothing. And that doesn't seem right. However, what you would find is that by increasing the number of loops in the coil of wire, it becomes more difficult to push the magnet into or to pull the magnet out of those loops. And this is because the induced voltage makes the current, which then makes a second magnetic field inside the coil, which will then repel the first. In other words, we do more work in inducing more voltage. So we are not getting something for free. This all leads us to something called Faraday's Law. And what Faraday's Law tells us is that the induced voltage in a coil going to be proportional to the product of the number of loops and the rate at which the magnetic field changes within those loops. So I have a graphic here on the right which kind of summarizes that. So right here is the voltage generated, and it's equaled to the number of loops, so that's capital N, and then the rate of change of the magnetic field. We use the capital letter B to measure magnetic field. So right here, this delta B over delta T, that is the rate at which the magnetic field changes. So delta B is the changing magnetic field, delta T is time, and anything over time is a rate. You'll notice it also depends on the area of the loops themselves. So what we could have is we could have a changing area. You know, the loops getting bigger or smaller somehow. That's usually not very common, so we don't usually worry about that too much. But I want you to see that it is, you know, proportional to the number of loops, capital N, times the change of magnetic field, delta B over delta T. This graphic also gives us some other ways of changing those things, so some different scenarios that you can take a look at. So then voltage can be induced in a loop of wire in three apparently different ways. First, by moving the loop near a magnet. Second, by moving a magnet near the loop. Or third, by changing a current in a nearby loop. By changing the current in a nearby loop, you're changing the magnetic field because electric currents flowing through wires creates a magnetic field. So in each of these cases, we have something that's important. A change in the amount of magnetic field in the loop. That's important. Well, now that we know that magnets and coils of wire can create electricity, we can now talk about generators and how these generators can make electricity. So when a magnet is plunged into or back out of a coil of wire, the direction of the induced voltage can alternate. So what we can think of is when the magnet enters, the electrons move in the wires. So when the magnet exits, those electrons will move in an opposite direction. So as the magnetic field changes, the induced voltage changes, or it alternates between a positive and negative, what we determine to be positive and negative directions. So we determined that one way is a positive voltage and the other way is a negative voltage. And honestly, it doesn't matter too much which one is which, but what's important to realize is that this changing direction of the magnet causes a needle on a gauge to deflect in opposite directions. And we define one direction as positive, the other direction as negative. So it's more practical then to induce a voltage by moving a coil rather than moving a magnet. And there's certain reasons for that. And there's different motor and generator designs, but we'll go with the first one. We're changing a coil. So one way we can do this is by rotating a coil inside a stationary field. And this arrangement is what we call a generator. So imagine that we have a handle attached to a coil, and this coil is spinning. As this coil is spinning, we can think of it as kind of cutting through those magnetic field lines, or the magnetic field inside this magnet. As it does that, it generates electricity. Another way we can kind of design this, we can have a rotating shaft. If you've ever been on a farm, there's PTOs. We can have splines on this, make it a PTO, and then we can turn this wire in this fashion as well. So the construction of a generator then, in principle, is identical to a motor. It's just that the roles of the input and the output are reversed. So any kind of electric generator can operate as a motor, and any kind of motor can operate as a generator. So when you forcibly turn the coils inside of a motor, you will produce electricity. When you apply electricity to the coils, it causes them to spin on their own. So electric motors and electric generators are basically, kind of the same thing. There's slight differences. As this coil rotates inside this magnetic field, the induced voltage goes from positive to negative. And what happens is we see a sine wave being generated. So when the coil is not cutting through any magnetic field lines, we have zero induced voltage. As the coil starts to cut through those magnetic field lines, that's when we start to generate voltage. And we can have a positive voltage, and then as it spins around and goes to the other side, then we get a negative voltage. So when we go to represent AC versus DC with a graph, AC is going to look like a sine wave, where the voltage is changing with respect to time, and we can use the sine function to explain that. DC does not change. It stays at a constant level. So a graph for the DC, or direct current electricity, is actually quite boring. There's not a whole lot happening here. The alternating current in our homes, because our homes run off of AC, is produced by generators standardized so that the current changes its magnitude and direction 60 cycles per second. So it has a frequency of 60 hertz. So what that means then is we see a complete wavelength, one of these, 60 times per second. So this time right here would be 1/60th of a second. So we would have one complete, between positive, and this is generally like positive 110, this is negative 110 volts. It would swing between positive 110 and negative 110 volts 60 times per second. So that's what that means by the frequency. All right, that's going to conclude video 1.